Yeah, sure.
All right, good afternoon, everyone. Thank you for being present and also wearing your mask. Just to kick off today's RSES seminar, we just want to acknowledge that we are, for many of us here, we are working and doing our research at the land of Ngunnawal and Ngambri people, and we pay our respects to the elders past, present, and emerging. Just a short announcement for next week's RSES seminar, we have Nadiv Dami from Curtin University that will be visiting us, and she will be talking about biomineralizations. And as usual, we'll send out the announcement, reminders, multiple, next week. And for now, I will invite Michael to introduce Callum.
Thank you. Callum did his undergraduate degree at UWA and is one of the rare ones who switched university for his honours, doing that in 2011 with Andy Hogg on ocean modelling. I met Callum electronically at the start of 2011 because I was responsible for signing some of the paperwork to do with it, but I never actually met him until the end of the year at his final seminar. So in that sense, he was an early adopter of the work from home strategy. After honours, he worked for a year in the resource industry in Western Australia, then attended Cambridge on a Gates Fellowship, if I remember correctly, graduating with a PhD in 2015 from Applied Maths and Theoretical Physics, and arrived back at ANU as first as a postdoc, then as a DECRA fellow, and more recently, I think Callum is possibly the first tenure track appointment in the university. He's currently responsible for the GFD lab, and his primary research area is sort of theory and lab experiments. And this work here is more at the theoretical end. So I'll leave it up to you, Callum.
Thank you, Mike, for that very nice introduction. So today I'm going to talk about what you can see here. So long-wave radiation and surface temperature. And this is one of those classic problems in earth sciences, in science generally, where it's a bit of a chicken and egg problem. So which came first, the chicken or the egg? I made the mistake when preparing this talk of Googling chicken and egg GIFs, and you'll see the results of that today. So hopefully they will entertain you, even if you get worn out by the science. In the background here, you can see a thermal image, and some of you might recognize this building. It's just over the road from us. It's the Florey building. And so I just wandered out the other day with a thermal camera and took this image. And what we're interested in today is actually the sky up here. So we're interested in the temperature of the sky, because that's what we mean when we talk about this long wave radiation. It's the radiation coming from the sky. And so the thermal camera sees that as a particular temperature, which is just saying it's receiving long wave from that region. So more technically, and I realize many of you will be familiar with this, but I thought I'd just go back to the basics and make sure we're all on the same page. What is this long wave radiation? So it's terrestrial radiation, so it's coming from the Earth system as opposed from the sun. And in the Earth context, it's these 3 to 20 micron wavelengths. So if you're looking in wavelength at the bottom here, in micrometers, this red patch is the solar radiation from the sun at very short wavelengths, and this band up here is what we call the long wave radiation. So it's really this quite artificial separation, but it turns out those two bands are quite neatly separated on Earth. So in climate science, we generally just band it together and say you've got short wave from the sun and long wave from the Earth system. So of course, these things are described by a black body spectrum, and that's this Planck function that's written here. And so that is actually the equation for these curves you can see in the background. And the difference between the actual spectrum and the curves is due to the absorption and emission by all the different gases, greenhouse gases in the system. The other important thing for the context of this talk is that if you integrate over the Planck radiation spectrum, hopefully most of you have seen this, you get a total energy under that curve, total wave number integrated energy, that's just sigma t to the 4. And that's what we would usually call the black body radiation, where sigma is this Stefan Boltzmann constant that is at the bottom here. So if we now think about, okay, well, how does this feature in the global energy budget for the climate, ocean, atmosphere system? You would probably more commonly have heard about long wave radiation in the context of the outgoing long wave, and that's this flux at the top here. That in a top of atmosphere sense, it's that balances the incoming shortwave from the sun, is balanced by this outgoing long wave. What I'm actually interested in this talk is not that component at all. I'm interested in this component that's coming down from the atmosphere to the ground, that we call the downwelling long wave radiation. An interesting feature is that if you think about increasing greenhouse gases, so we increase the gases in the atmosphere here, then most of you would know that initially that actually decreases the outgoing long wave radiation, which leads to heating and global warming. But at the same time, it actually increases the downwelling radiation at the surface. So we think about how this changes under climate change. Then here's some predicted changes in the surface fluxes down here from one of Michael's papers that's analysing CMIP3 models, so a few generations ago now. So this was under one of the high emissions or high to moderate emission scenarios. And you can see under those, you've got an increase in this downwelling long wave radiation surface of 19 watts per square meter. And that is essentially balanced out by predominantly in these models, a radiation back from the hotter surface and some evaporation, some additional evaporation from the surface. And that keeps this budget balanced. There's some other small changes, but those are the two main ones. So you can see the biggest perturbation under these sort of climate changes to the surface balance is actually this downwelling long wave radiation. And that's why we're really interested in it. So to put a bit more formality around that, the actual surface energy balance, so if you go to any point on the surface, I'm going to think more about the ocean case because that's really the space I like to work in, but you could think about the land surface as well, if you prefer. This is what your surface energy budget looks like. So this is all the fluxes going in and out through the surface. So you have essentially your shortwave coming in with a reflected component that gets shot back up. You've got this downwelling long wave we're interested in. There's a sensible heating, or sometimes called a Newtonian cooling. There's an evaporation, so the latent heat flux. And then there's this outgoing long wave. So the surface is radiating back up into the atmosphere. And all that added together gives you a net flux in. And that flux is, in this case, we think about the ocean. That flux is then dealt with by ocean dynamics, taking that heat through the ocean somewhere else where it'll pop back out. So that's how this balance works out. Each of these different terms has a particular expression. Most of them are, many of them are approximations or empirical relations, shall we say. And so if you think about that, well, the net shortwave is essentially, if you ignore clouds, it's kind of fixed by the sun at a given time of year, you get a given shortwave. The sensible heating scales with a temperature difference. The evaporative cooling scales with a vapor pressure difference. And the outgoing long wave is this black body spectrum, so it's Ts to the 4th. You'll see what we're missing here as well. What's this downwelling long wave radiation? How does that scale? Well, that's kind of the question I want to address. So what sets this radiation? So if we go to how is this figured out in a climate model? So climate models, of course, do this all the time. It goes into a thing called a radiative transfer module. And so how that works is you have a stack of atmospheric layers, which are the layers in your model. And each of these has a temperature, it has a pressure, it has a concentration of all these different greenhouse gases. And associated with each of those greenhouse gases at a given temperature and pressure, there's a certain absorptivity or emissivity. And that's something that can be measured in a lab and put into essentially a database. And then what the model does is propagate radiation through this system, looking at these absorptivities and emissivities, which are actually equal, and look at the the total radiation coming down through these different layers and gets the total downwelling long wave at the Earth's surface. And that's governed by these equations. You don't need to worry about the details. These are called Schwarzschild equations. And so the model essentially solves these equations. So the emissivity, so the amount of emission from each of these different layers, is determined by the concentrations of all the greenhouse gases sitting in those layers and the temperatures and pressures of those layers. So it depends on the full atmospheric structure. It's all very complicated. It's a black box. You put it in, you get an answer. And if you have clouds, it gets even worse. I won't talk too much about clouds today, but Ko here is a new honours student. He's going to be looking at the clouds role in this budget. Okay, so here's just to make it a little prettier. Here's what it looks like. So this is the downwelling long wave radiation from January 2016 globally. On the left, I've shown you what it looks like when you don't have clouds. And on the right, what it looks like when you do have clouds. And of course, because this is actually from a model, you can play these games where you can just say, oh, let's just get rid of the clouds and see what the radiation would do. And that's what's being shown here. So you can see that the clouds actually increase the radiation generally. So what this is really showing you, as I mentioned before, is the sky temperature. It's showing you how hot the sky is. And a little comparison over on the left here is a picture of clouds in the sky, and you can see where the clouds are, it's warm, right? And that's just because the radiation level when you have clouds is lower down in the atmosphere where it's warmer. This is coming from the clouds. Whereas if you're looking through clear blue sky, the radiation is a lot higher and colder. So we can think about what happens if we play a bit of a game now. Let's suppose we have this climate model and we're going to do the classic climate experiment. We're going to put in some more greenhouse gases. So what does that really mean? Well, it means we're increasing the emissivity alpha here of each of these layers. And if we think about doing that, okay, we've got higher emissivity. That means that these layers have more substance that's generating this radiation. So the radiation is increased. Think of that maybe like the egg. And if you have more radiation coming into the surface, thinking back to that surface energy balance, it means the surface gets hotter. So we have a higher TS, a higher surface temperature, and that's your chicken. But of course, the surface is coupled to the air above through all those fluxes we mentioned. We had sensible heating, we had latent heating, we had radiation back to the atmosphere. And so, of course, then the temperature of the air above the surface heats up again. But once you do that, that then radiates more back down. And so you've got increased DLR. So you've got this more increased downwelling long wave radiation again. And around we go. Okay, so we get into this feedback loop where a small increase in the greenhouse forcing amplifies downwelling long wave radiation, which amplifies the temperature and so on and so forth. And so it's these chickens running in a circle. So this feedback loop is what we really want to understand, right? So we've got this initial increase and then we put it into this feedback loop. How can we decompose the different effects here? And I should point out that it's not the only thing you'd want to think about is what happens if you increase the greenhouse gas concentration. You might also think about what happens if I change ocean circulation. If you're an ocean modeler, this is what you care about. You change some ocean circulation, say from this state. This is a picture of the Gulf Stream. It transports a huge amount of heat northwards. So we change that and suppose some ocean dynamics lead to an increase in that northward heat transport. We're then going to have an increase in the radiation coming out of the ocean in the North Atlantic. And we might want to think, well, how does that influence the surface temperatures and the downwelling long wave there? And so it's the same process. It's just you jump into the loop at a different point. So you're increasing an ocean heat flux here. You'll make the surface hotter, higher surface temperature, higher air temperature, greater downwelling long wave radiation, increased surface heating, and around we go again. So these are the things we'd like to decompose and understand how much is actually from these initial changes versus how much is this feedback loop going around. Why is that particularly interesting? Well, because if you're not a climate modeler, but you're an ocean modeler, instead of having this feedback loop where the chickens go around in circles, the chickens stop because you fix the air. Your atmosphere is fixed. So instead you heat surface temperature and the atmosphere just stays the same, and that's the end. So the fact that you ignore this feedback loop in an ocean model means you're going to get quite a different response. And one might question whether that's important and something we should think about. So I'll come back to that at the end. So the outline then is really, firstly, we'll go through a model for this downwelling long wave radiation so we can actually understand what it depends on instead of using these black box radiative transfer codes. And we'll use that to look at forcings and feedbacks in a climate model simulation, so in CMIP simulations. And lastly, I'll mention what some of these implications of this work are for ocean models, essentially, and studying ocean circulation. So if we go to downwelling long wave radiation models, there's a bit of a menagerie of these things. So this is a pretty hard thing to measure. And as it is noted here, it wasn't measured until the 1970s. And it's only routinely measured since the late 1990s. And the longest measurements are from starting in 1993 in Switzerland. This is a really, downwelling long wave radiation is a really challenging thing to actually measure. An example of the measurement is shown in the picture here. So this is actually a picture of Mike's setup that was at the Canberra airport about a bit over a decade ago now. And this is an evaporation pan, but up the top here, circled in red, you can see a little device, which is actually shown up the top here. And so this is a radiometer. So this measures both long wave and short wave radiation. And this is sort of the standard equipment that is now put on these measuring stations. So of course, in theory, you can calculate this from the radiative transfer code. I've already shown you how that works. The problem is, to do that, you need full depth profiles of temperature. So you need temperature at every pressure. You need concentrations of greenhouse gases, so you need water vapor, CO2, everything at every pressure. I mean, that's even harder to get than just measuring the long wave radiation. So in practice, it's not something you can just go, oh, I know what the downwelling long wave is. It's actually quite a challenging thing to get. But it's actually also very important because of its role in the surface energy budget. And historically, it's been very important for agriculture and water resource studies, particularly around crops and looking at the evapotranspiration from crops. As a result, everyone came up with their pet formula for it. And I really do mean everyone. So this is 2009 paper where they basically amalgamate and list all the different formulas people have come up with, starting in 1918. So about 100 years worth of formulas. You'll see that they've all got a lot of similarity between them. So they all depend on essentially properties like the temperature, the humidity. Some of them depend on saturation vapor pressure, which is just a different way of measuring the humidity. And they're all sort of formulated in this way where they've got something they call an emissivity multiplied by the black body radiation component. So basically the sky is some fraction of a black body radiation. If it was a solid object, it would just be a black body, but because it's somewhat transparent, it's some fraction of that. So I mentioned, yes, they all depend on some combination of these different variables up here. And none of those ones that were listed there have any reference to greenhouse gases other than water. So this is already telling you water is the most important thing for determining this. But we're interested in what happens in a climate forcing scenario where you increase the CO2. So they're not that useful for our application. And the other problem, of course, is that none of them work everywhere. And I like this classic quote from this Gao et al. Paper, that basically a method that can be successfully applied everywhere does not exist. And so this is a great call to further work in my mind. So the problem essentially is you can tune these formulas for your one set of data, but if you go somewhere else, they don't work. So they're all customized and tuned for a particular data set. And you can kind of see that from all these empirical parameters littered through the formulas. Okay, so if we want a new theory for this, how do we do it? Well, or what do we want to achieve here? Well, we know we need to include water vapor because it's the most important. We also want to include CO2 so we can look at these climate forcing studies. We want it to work everywhere without having to retune it. That would be good. And ideally, we'd like to start from the actual physics rather than just coming up with yet another scaling relation. So how do we do that? Well, we do the physicist's approach, which is simplify everything to the maximum degree possible. And so on the left here, you can see plots of something called the US standard atmosphere. This is basically the average atmospheric state. I'm just using this as an example. So the temperature decays with height. That's just the lapse rate. Water vapor is concentrated near the surface. The surface is down at the bottom here, and this is just 25 Ks at the top of the plot here. So water is concentrated in the surface and decays exponentially with height. And similarly, CO2 is actually concentrated near the surface. And that's simply because the density of air is higher there, therefore the density of the CO2 is also higher. And so with each of these curves, you can associate a height scale, which is just the E-folding scale. And so what we're going to do is pretend that these are just stepwise approximations. So we're just going to shove all the water in this essentially 3 kilometer thick layer at the bottom and have this red curve here, same for the CO2. And if you do that, it's quite natural to say, well, actually, this is just an atmosphere that has 2 layers. The bottom layer has CO2 and water. The layer above at some different pressure and temperature just has the CO2 in it. And it has air, but we don't care about that. We just care about the radiatively active components, so just the greenhouse gases. So now you have a 2-layer model, which you can plug into this to a radiative transfer code and see what happens. So if you do that, you get these outputs basically. And so these, again, you can see that black body curve we were talking about before. And you can see absorptions or departures from that black body curve. And what I've done here is split this into 3 components. So this, if you look at the diagram at the bottom here, we're looking at the radiation that's seen at the bottom surface here. And that's this, this L1. And that's the radiation that's coming from that lower layer. So it's coming from this bottom layer to the surface. For comparison, the L2 naught is the radiation that's making it all the way from the top layer through the bottom layer to the surface. And that's this red thing here. And the point of this is that it's minuscule. So actually the radiation from above this bottom layer is so moist and so rich in a greenhouse gas, water vapor, that the radiation from above doesn't come through. And actually it's far less than 10%. It's typically a couple of percent. And so what we conclude is, well, we don't actually really care about that, and we'll just throw it away. And so we just get a 1-layer model. It's much easier. Who wants 2 layers when you can have 1? And so the radiation at the surface, we've just shown a simple experiment to show it's actually entirely determined by the properties of the near surface air, with some height scale associated with the height that water vapor goes in the column. So that's quite convenient. So once we know that, we can actually essentially figure it out. And the way you do that is if you go back to those equations, those Schwarzschild equations I was talking about, you're essentially adding up the emissivity from this layer. And that involves adding up along all different viewing angles from the surface. So if you're sitting at the surface here, you get radiation from above, but you also get radiation from the whole hemisphere. And so that's all this equation here is really saying. It's saying you have to add up around the whole hemisphere to get the total radiation. And at the moment, we have these 5 parameters. I still think 5 parameters is too much, to be honest. It's a bit painful. We don't really want that. So it turns out the temperature dependence of the absorptivity is almost nothing, something like 1%. Let's get rid of that. The pressure dependence of the absorptivity is also, it's important, but it's also very predictable. And that's because of this thing called pressure broadening. So basically, if you have 0 pressure, spectral lines are just a line. But as you introduce pressure, it broadens the spectral lines. And that changes the absorption properties, because you can now absorb multiple wave numbers. So you actually get more effective radiation generation and absorption at higher pressure due to that effect. The other trick we can play here is introduce this idea of a representative angle. So instead of thinking, oh, we have to integrate over the whole hemisphere, we say, well, the hemisphere average radiation is the same as looking at one particular angle, which has to be true at some angle. It's just a question of what that angle is. So that angle is called this theta r, and that becomes our one and only tuning parameter in this system. We just pick the theta r that gives you the correct hemisphere average radiation. So if we do that, we find out it's 40.3 degrees. Wonderful. So we have to look at that angle. to get the correct radiation. And we get this effective height, which just depends on this sort of mean path length along this angle. And it has this pressure factor, which is the thing I mentioned, that these spectral lines get broadened under high pressure. Okay. So we can then say, well, let's go and do what everyone else has done and write this as this black body generation by this function here that's less than 1. So it's some fraction of a black body generation. And the only question is, well, what is this factor here? And this tau we call the optical depth. So it's the optical thickness of the layer. And if you think about it, if you have a very optically thick layer, that means this tau goes to infinity, which means you just get a black body spectrum. If you have an optically thin layer, so you get rid of the atmosphere entirely, that goes to 0 and there's no radiation. And you're just essentially mapping between those two extremes. The cool thing now is that we only actually have 3 variables left in this system. We've got the specific humidity, so that's the concentration of water vapor. We've got the CO2, and we've got this height scale. So how high is the water in the column? And that's it. So we can now essentially span the parameter space very easily, because there's only 3 different parameters we need to investigate. And so that's exactly what we did. And here's an example. So here's different CO2 concentrations. And this is showing you a color plot of what the optical depth looks like. On the y-axis, you've got the height scale. So this is how deep your single layer is. And on the x-axis, you have the specific humidity, so concentration of your water vapor. And this, once you've got this optical depth, you can plug it into the formula to work out what the downwelling long wave radiation is. One interesting thing you'll notice here is there's very little difference between the different CO2 concentrations. You have to look really hard to see that there is in fact a difference there. And we'll come back to that, but that's essentially implying what we kind of already know. The water vapor is the most important, and the CO2 in and of itself doesn't actually do much, which implies that the changes that you see, if they're big, they're actually a feedback. They're not directly from the CO2. And I'll come back to that a bit later. Okay, so we have this model. How does it do? Well, here you go. Here's a validation against this reanalysis product called ERA5. And so this is hourly data. So we've just compared how does our model do in the prediction versus these hourly observations. And the error is plotted here. And here's just a histogram showing you how the model behaves. And it does very well. So the average error is about 3%. Works particularly well over the ocean, which is great for me, because that's primarily what I'm interested in. We can also validate it against observations. The challenge with observations is, as I mentioned before, this height scale of the water vapor, we don't really know unless you go and measure that, but then that's another challenge. So what we do is cheat and just say, well, it's equal to this ERA5 data set. So this is a reanalysis, it's kind of observations. And we just say, well, it's equal to this climatology. And we'll assume that that's true. And that turns out to be a pretty good approximation because this height scale doesn't really vary too much. So if I go back to the Canberra evaporation pan I showed you before, we can look at some data from that. So if we look at the water vapor height scale over Canberra, that's 1,850 meters, it turns out. So that means your e-folding depth of water vapor, you look up in the sky now, is 1,850 meters. So you're getting essentially 2/3 of the water vapor when you reach that height and only 1/3 above it. And if we use that value, we can see that, in fact, the predicted and observed match up very well. So indeed, this approach works quite well. The errors tend to be a bit bigger because this is real data, not this model data. Unless you think, well, the height scale doesn't really matter, I can show you how badly the model does if you change this height scale away from the climatology value. So the X is the climatology, and this shows you the error if you move away from that. And you can see if you move a moderate way away, the error gets very large very quickly. So it is actually very sensitive to this. It just turns out we can predict this very accurately from the climatology. So to summarize that, What sets this downwelling long wave radiation? Well, primarily it's the near surface air temperature and the near surface specific humidity, or the concentration of the water vapor. And then it's also the height scale of the water vapor and the CO2 concentration in this near surface layer. So the cool thing about this new model is it does apply globally. You don't have to retune it. And for comparison, this is the error associated with the best previous method according to this paper. And here's the error with our model. You see it's a little bit different. And this is physically based, so we've built it up from sort of first principles, and we've included CO2, which is very useful for what I'm going to show you next. So forcing and feedbacks. So when you run a climate model, you've essentially got some initial state over here. You plug this into this wonderful black box called a climate model. You throw in some forcing from, say, CO2 at the top. The chickens in the model do their dance, and out pops a final state. It doesn't tell us what contributed to that final state. Was it directly due to this forcing, or were there feedback processes in there that gave rise to that particular outcome? So that's essentially what we'd like to disentangle. And fortunately, the sort of idea behind this was done by Brian Soden and Isaac Held. And it's actually pretty simple mathematics. It's just saying, well, if you have a function that depends on a certain number of variables and you want to look at small changes, well, of course, you just do a series expansion, right? And that's what's shown here. So the change in some function is the derivative with respect to each of those variables by the change in each of those variables. And this derivative term in these analyses is often called a kernel. So particularly if you're interested in radiation, they call this the radiative kernel. Terrible nomenclature in my view, but that's what people have called it. It's really probably better called just a feedback parameter. And the idea is generally this feedback parameter is telling you about the physics of the system. So it should essentially be model independent. It should be independent of the magnitude of the change. So whether you have a small change or a big change, it's still the same. And with this, you can attribute a change in whatever you're interested in this case, downwelling long wave, to changes in each of the physical parameters, so temperature and humidity, for example. And so you can untangle these feedback processes. So, I mean, this is a great idea in principle, but there are challenges with it. Because in general, of course, this thing you're interested in, you don't know what everything it depends on. It could depend on a whole range of things. It could depend on anything that's in the model. And so you can't fully close the problem in principle unless you test its sensitivity with respect to everything. And of course, each of these variables I've just set up depends on T and Q. But of course, T and Q have a different value at every grid point in your model. So really, it depends on T and Q at every single point in your model. And that means that you need to do complicated 3D calculations to work out what these derivatives are. And the data in standard model output is usually not available, so you may not even be able to do that. However, it has been done by a few people. So it's been done for outgoing long wave radiation, which is the top of atmosphere radiation going back to space. And that was in the earlier 2000s. And then it's more recently been done for this downwelling long wave at the surface. So to compute each of these derivatives is kind of how you do it is shown in these little schematics at the bottom. But essentially every little grid cell in your model, you have to increment by, if you're looking at temperature, you increment one level of your model by 1 Kelvin, and you rerun your radiative transfer code to see what happens at the surface, and that gives you the derivative. And you do that for every single grid cell. So could be a bit frustrating, and it's certainly complicated. Oh, and this is what a sample feedback parameter or kernel looks like. Now we've kind of got around all this because we now have an explicit formula for this thing we're interested in, which means we genuinely just take a derivative because we have the formula. It's not, we don't have to do any modeling craziness. We have a formula here and we know it depends on a finite number of parameters. And so we literally take the derivative of each of those 4 parameters, and that's it. We can write down explicit expressions for each of these so-called feedback parameters, or kernels as people like to call them. And it usually gets written in this sort of way. So you've got a change in this downwelling long wave that we're interested in is a radiative forcing, and this is the direct increase due to the fact we increase CO2. And then there's feedbacks due to temperature, water vapor, and the height scale. And all of these things are available in just 2D standard climate output, like all the CMIP models. To put that a bit more visually, the different things we can do, we can put in extra CO2, which gives you extra radiation down. We can make it hotter, which gives you this temperature feedback. We can make it wetter, which gives you this moisture feedback, or we can make this layer deeper, which gives you this atmospheric structure, or what I call the height scale feedback. One thing I'll point out is that usually these two middle ones, hotter and wetter, go together. And that's because if you have a constant relative humidity, which is often assumed and turns out to be a pretty good approximation, then the humidity just scales with the saturation vapor curve, which is plotted here. And that is just an exponential curve where the humidity increases at 6.5% per degree. And this is called the Clausius-Clapeyron scaling, or the CC scaling, you might have heard it called. And this is the moisture feedback that people often talk about in the context of climate change. So we can use this to analyze CMIP models. And so that's what we did here. So we compared an initial period, which is 06 to 2026, to a final period at the end of the century. And we looked at these 5 different models under the high emissions 8.5 scenario and calculate the different mean states and the changes. So this plot is just showing you the mean climatology in the initial state. So you can see that there's the models are fairly consistent, although there are particularly changes once you start looking at things like the height scale and the clouds, whereas the surface variables are quite consistent. Note that I'm only showing you 3 of the 5 models because that's all that would fit on the page. And then the first thing to do with these is to confirm that actually our theory can get you the right magnitude of the change. Before we look at the individual components, we want to double check that actually, if we sum up all these components, we get the observed or the model change correctly. And so we can double check that. And so here's the CMIP output that gives, that's what it gives for the change in this downwelling long wave. This is our calculation for each of these models. You can see there's a lot of variation between the different models, but we accurately capture the changes. So this is just the difference, and then a histogram showing you that in fact, we can capture these changes. And I'd emphasize there's no tuning in that. That's just the model I pitched before, hasn't been retuned or anything. That's just raw what it does. So once we believe that that's working, we can decompose the different feedbacks. And so that's what I'm showing you here. And again, these are the differences. This is temperature, water vapor, height scale, and the sum of all the feedbacks. And although the changes themselves, which I showed you previously, are quite different, the feedback parameters are all fairly consistent, which is going to that thing I said, that these things should be model independent because they go to the actual physics of the system. So if the physics are the same, they should be the same. There is an exception where the height scale is actually quite different. And I could show you over the different models how much each of these parameters vary. So here in this new plot is the standard deviation between the 5 different models in each column. And this is the total standard deviation. And you can see it's pretty much entirely dominated by this height scale feedback. And so you can trace the changes or the differences between the models can all be traced back to essentially differences in the climatology of their depth of water vapor in their initial state. So they actually all have different height scales of water vapor now in the present climate, and that translates into different changes in the downwelling long wave radiation over the next 100 years. And in a sense, that's possibly not surprising because while modelers will tend to tune the hell out of surface parameters, they probably don't look at the atmospheric structure too much. So those were plots showing you globally what it looked like, but we can now, we're showing you spatially what it looked like, but we can also just look at the sum globally. And so this here is showing you the global mean of each of those feedback parameters. And as I pointed out before, the variability is arising through this height scale. It's not arising from the temperature or the water vapor feedback, it's through the height scale feedback. Even though that's the smallest one, it's responsible for the most variability. And you can see the feedbacks are relatively consistent, whereas the change in the downwelling long wave in each of the different models is hugely different. But that's not because their radiation is different, that's because they had different changes from other effects like dynamics, for example. And the radiative forcing you can see over here, and you can see the radiative forcing is like 3 and a bit versus a total change of 20 to 30. So the direct radiative forcing is about 10%. Almost all the changes is feedback loop. I won't say too much about clouds other than to say you can do this for clouds as well. And so this left one is the one you've seen before. This is for no clouds, and the right one is for clouds. The results don't really change a huge amount, but you can ask me about that later if you want. So to summarize that section, we have a methodology that you can apply really easily to diagnose these forcing and feedbacks in climate model simulations. You only really need to know the 2D fields that are standard output. And the accuracy is actually just as good as these complicated previous 3D methods. And importantly, 90% of the response in this change in downwelling long wave is actually due to this feedback loop. So only 10% is coming from the increase in CO2. The rest is this self-amplification through this loop. So the last thing I want to talk about is, well, what does all this mean if you want to run a decoupled model like an ocean model? So if we go back to this balance we had initially, this is the surface energy balance we were talking about initially. What I'm interested in here is thinking about, well, what happens if we change the ocean dynamics? What's the response of the surface? So the thing I would point out here is that in a coupled system, the air temperature actually follows the ocean temperature. And this is just a question of heat capacity. The ocean, even just the surface ocean, the mixed layer, has an enormous heat capacity. The air, even the whole atmosphere, has a very small heat capacity. And so if you bring a different temperature atmosphere in contact with the ocean will change by 90% of the difference. The ocean will change by 10% of the difference, and the air will change by 90%, right? Just roughly. And so that's what we meant when we were talking about this loop where the surface is coupled to the air above, that a higher surface temperature of the ocean means a higher air temperature above. So that's important because in an ocean model, we won't have that feedback. I'll come back to that in a second. If we look at this balance we've derived above, or this balance here, and we look at small changes from this balance. So we're thinking about putting in this small increase in ocean heat flux delta Q, that's here. We don't have any change in the short wave. We've got a change in the downwelling long wave because we've got a change in the surface temperature and therefore a change in the air temperature. That's this delta T. And there's these feedback parameters, which we already figured out. And we also have a change in the evaporation according to this, blah, blah, blah. You can solve this to get an expression for the change in the temperature. And the point here is that the evaporative feedback and the outgoing long wave feedback tend to cool the surface back, right? So if you increase the temperature, the evaporation will become stronger and it will tend to cool the surface. If you increase the temperature, the outgoing long wave will become bigger and it will cool the surface. But if you increase the temperature, these downwelling long wave feedbacks will act to warm the surface. So they are a positive feedback, which is acting to increase this change in temperature. So let's think about the ocean case. Well, what do I mean by this decoupled model? Well, in an ocean-only model, what people usually do is they treat these atmospheric fields as just forcing products. And so they let their surface temperature of their ocean vary dynamically, but all these other quantities, the air temperature, the humidity of the air, the downwelling long wave, the short wave, the wind speeds are all fixed. They're all set by this atmospheric forcing product. So going back to our little feedback loop, that means you no longer, when you have a higher surface temperature, you no longer have a higher air temperature. Air temperature is fixed. You can't have this feedback happen. So the question is, well, what does that mean for this temperature change delta T induced by this change in ocean circulation? So we can repeat the little analysis we did before and work out what this this delta T would be. And in this ocean-only case, all of the feedbacks suppress the temperature change. There's no longer this positive feedback from the downwelling long wave because you can't change the air temperature. So if you compare those two cases, it should be pretty clear if you just look at these two equations that the coupled solution has a much, much bigger temperature change than the ocean-only. And the question, well, how much bigger? Well, we can put in some values and find out. So here are some typical values. Let's see. A lot bigger. It's a factor of 10. So when you run the coupled model and you have this change in the ocean dynamics, you get 10 times bigger surface temperature change than in the ocean-only model. And so this suggests that maybe for certain problems that you might be interested in, it's a bit of a problem with the current configuration of ocean-only models. So if you're interested in something that really the surface temperature is crucial, say you're interested in sea ice coverage, where it's pretty important what the surface temperature is, then running an ocean-only model in the current configuration might not be the smartest strategy. So is there a better way to do it? Is there a different way to do it? Well, I'd suggest maybe there is. So the current method is to say, well, you fix the air temperature, and then you go and calculate this evaporation and sensible heating using the formula. What I'm suggesting is maybe instead of fixing the surface temperature, you just fix the difference between the air temperature and the surface temperature. And that correctly incorporates the fact that, in fact, the air follows the ocean because of the relative heat capacities. So it's a very tiny change, really. Instead of just fixing that air temperature, you fix the difference. And that would allow you to include this, this local feedback due to the downwelling long wave as well. And so the open question is, well, if you did that, would this give you a better picture of some of these ocean dynamics and allow you to address certain questions in a better way? So to summarize, part one, we had this new analytic or semi-analytic model to look at the radiation from the sky down to the surface. And we came up with something that actually applies everywhere with a very small error. An extension to account for clouds is under development as of about 4 days ago in a new honours student. The model allowed us to interrogate this energy balance at the surface, and in particular interrogate the forcing and feedbacks of the downwelling long wave in climate forcing scenarios. And we showed that 90% of this change in the downwelling long wave is actually this feedback loop. It's not a direct forcing. And that means you need to be very careful if you're thinking about future climate change and decoupled models. You shouldn't treat this downwelling long wave as independent forcing. It's not. It's coupled to the surface temperature. And maybe that led us to a new way we could think about forcing ocean models for certain problems. Okay, thank you.
Pretty sure lots of people have many questions to fire for you, but then for those who are online, feel free to raise hand or pop your questions in the chat, which I'll put it on the screen now so that people can see. Then, and all right, Ashley.
Thanks, Callum. I was wondering about the angle you chose as your average model. It seems pretty magical. How much does it depend on, like, depend much on the time whether you're averaging over, or does it change seasonally?
No, it doesn't change at all. It's just fixed globally.
Fixed globally.
Well, look, we could make it change. I mean, you could tune the hell out of the thing and make it a variable, but then that you're just making that up, right? Yeah. Whereas you say it's fixed globally, at least you're not imprinting any sort of false structure to your model. All the structure comes from the fields that are input to the model. You're not adding a structure through the tuned parameter, essentially. So yes, we just treat it as globally fixed. Interestingly, it actually agrees with previous studies where they've looked at this problem and they've actually said, let's point a radiometer in different directions and see at what direction should you point it if you go out in the field to get the right radiation. Once you do a bit of the, once you account for the pressure differences, turns out we actually have the right angle. So there's a physical basis to that number as well.
And Andy has a question. So do you want to unmute yourself and speak out loud, Andy?
Sure. Can you hear me okay there, Callum?
Yep, can hear.
Yeah, okay. So very interesting. I wanted to comment on the ocean model forcing because I actually think the situation is much worse than you painted. So, I mean, specifically for sea ice, right? And the reason is that when we actually force these ocean models, we actually give it an output from a reanalysis, and that reanalysis will know where there is sea ice. And so the air temperature above where there's sea ice in the reanalysis will be 20 degrees colder than where there's no sea ice.
Yep.
And so there's actually an infinite heat capacity source of cold there that really fixes the sea ice really accurately. The other thing is that the inputs to the model also include the downwelling long wave.
Well, only
Actually.
because you choose them to. You don't have to.
Well, sorry. The standard set of fields that global large-scale ocean modelers use to drive global ocean sea ice models include the downwelling long wave.
Yes.
Right. So,
and that's just amplifying the temperature effect you're talking about, because that is actually being set by the surface temperature, which over ice would be really cold. Therefore, the downwelling long wave radiation is really small, and that's again pushing it to have ice there. Exactly.
Right. And it's so constraining that in times where we have tried to do greenhouse gas simulations, it's not enough to increase the temperature. You've also got to change the downwelling long wave, and you've actually got to change the specific humidity to get the right answer. But that leads me to a question, which is that if all you have is an atmospheric reanalysis state and you want to use that to force the model, are you saying that you need to say, go back to the reanalysis and find delta T? Or are you saying that it would, so that's one possibility. The other possibility is to have like an atmospheric mixed layer model, which varies in time and can allow you to calculate a delta T. Do you see the distinction between those two? And do you have a gut reaction as to which would be more effective?
Yeah, so I would suggest you go back and calculate delta T, but coupled with that, you'd also you'd be calculating the downwelling long wave at each time step using the formula we have, which gives you it as a function of that air temperature, which you'll now be calculating based on the delta T of the surface temperature, the specific humidity, which will follow the surface temperature according to the saturation curve, because you'll just assume the relative humidity is the reanalysis. So it actually doesn't vary much over the ocean. So it's a pretty safe assumption. And I think that's actually it. That would be the only changes. So I don't think it's that hard, to be honest.
Well, but do I understand you correctly? You couldn't do it without going back to the reanalysis and getting that delta T.
Yeah, you need the delta T, or you make some assumption and set a delta T. But yeah, ideally you get the delta T. Yes.
Yeah. Okay. Thanks.
Yeah.
It's sort of the same question as Ashley asked. So I don't think maybe I understood incorrectly. So you have to integrate the downward long radiation at essentially all different angles, right?
Yep.
So if you're integrating at all different angles, how could you find an angle which is representative of the entire radiation? Does that make sense? Like, if it's an integration, then by one angle would be representative of the entire field.
Yeah, so it's one angle, but then it's multiplied by the area of sky, basically. But the point is, if you look at the whole radiation, right, you can think about it in a certain direction. Let's say horizontally, there's nothing. And we go up and up and up. There's actually some maximum, and then it reaches some intermediate, and then it goes back as you go over the other side. Over that range, you guarantee that the mean is one of those values. It has to be, and so that's the angle we're finding. It's just the one that gives you the mean over that whole arc.
Thanks.
Jeff.
You can repeat the question.
Oh, okay.
Again, it raises question too clearly, so I'm just hoping that maybe you can phrase it for yourself.
When I repeat it to the Zoom
Yeah,
audience.
exactly. So, the cubic Earth system model has this energy moisture balance model. It's like a jelly atmosphere on top of the full 3D ocean.
Yeah.
I'm wondering how what you're suggesting differs from that.
Depends. So Jeff asked about I think this is similar to Andy's comment actually about having some sort of single level atmosphere over the top of the ocean and how this would differ. And well, does that have dynamics in the atmosphere? I suppose would be the question.
It's very parameterized.
Yeah, so this has zero atmospheric dynamics. You could argue it has atmospheric thermodynamics because you're dealing with the radiation, but it doesn't have any dynamics at all. So you've decoupled from atmospheric dynamics. The other difference would be, I don't know how they calculate the downwelling long wave in that model, but I would guess it's not particularly accurate, simply based on it must presumably is one of those previous formulas or it's fixed, and those previous formulas don't actually work very well globally. So my guess would be perhaps you could do something like this to improve that calculation, downwelling long wave. But it does depend whether you want to decouple from the atmospheric dynamics entirely or not, which is generally the rationale for using an ocean model, at least in part, is you want to just look at the ocean effect rather than getting influence from atmospheric dynamics.
I guess could be a naive question. So
That's
you show
good.
an example of measuring this long wave radiation on surface, but
Yeah.
how would you do that for ocean?
Yeah, I suppose you can put this contraption on a ship. But yeah, this is a problem. Ocean data. People just generally, it's hard enough to get it on land. When you go to the ocean, people generally just don't, to be honest. And that's part of the problem, is that the amount of high quality data in this space is pretty small. So I showed you one example from the Canberra Airport data set. There's actually a relatively small number of other ones we found, maybe about another 20 FluxNet, which are these flux tower sites where they have a similar setup, but they're all on land. And yeah, there's not that many of them. This is a problem, and there's nothing actually genuinely on the ocean that we could use.
So that means there's no sort of like a remote sensing technique for these kind of measurements at the moment.
Okay, so there is some. There is calculations of long wave from a satellite. It's called the International Cloud Climatology Project. There's some there, but again, that is actually a model that's being applied to the data. It's not a direct measurement. So, yeah, how much you want to take that as gospel is open to interpretation.
Any more questions online or in the room? If not, maybe I'll just have another question and then we can end.
Sure.
So for the so we look at a lot of factor data sort of model on ocean, and then sort of ocean surface probably is simple, but then for land, do you consider sort of vegetation, or is that just got sum into the surface temperature factor?
So do you mean in terms of
sort of like your boundary condition? Like?
Yeah. So I mean, for the actual calculation here, the thing that goes into this model is the air temperature. That's fine. The problem with land surface comes if you want to think about this this idea of a decoupled model and these feedbacks. The land surface, you can't really make this argument I made for the ocean that the air temperature follows the ocean temperature. So the land surface also doesn't have that high capacity. So I mean, you will know this, the air temperature over land varies hugely over a day. It's not the same over the ocean, it's very different. And so that makes applying this sort of this idea of how to force a decoupled models and how to untangle these forcing and feedbacks over land, it makes it a lot more complicated, to be honest. And how one would do that, yeah, I'm not sure.
So with that, let us thank Callum again for his wonderful talk.